This is our video on functions. Later in the course, in future modules, we're going to see natural phenomena that can be approximated using functions. In this video and in this module, we're simply going to look at exactly what functions are. So a function is a rule that takes numerical inputs and gives for each input a numerical output. They are usually described, usually given single letter names, and are usually described by using equations. So looking at this example, f of x equals 2x squared is a description of a function. The letter f is the name of the function. X represents a typical input to the function. The left side of this equation is read f of x, and it means the output of the function when the input is x. In other words, this means that you plug the number x into the formula. On the right-hand side of the equation, the formula 2x squared is the rule for calculating the output when the input is x. We'll be looking at lots of examples shortly. So here's sort of an oversimplified version of what a function is. For many purposes, you can just think of a function as being a formula, like 2x squared, for formula for doing a calculation. Although sometimes functions are described by using tables. Here's an example of a function described that way. So in this table, the inputs are listed in the top row, the row labeled x. So the possible inputs are -2, -1, 0, and so on. And the corresponding outputs are listed in the second row of the table, the row labeled f of x. So when the input is 3, for example, the output, f of 3, will be 7. And when the input is 5, you locate 5 in the top row of the table, and the number below 5 gives you the output. f of 5 is 11. So when a function is given by a table like this, we have to assume that the numbers listed in the top row are all of the possible inputs. And sometimes all we will have is a verbal description of a function, which is really no help at all in calculating. We might see something like this, for example. Let capital F of P be the temperature at Willow Run Airport on December 3rd, 2019, T hours after midnight, in degrees Fahrenheit. This describes what F of T is in words, but doesn't give us any idea of how to do a calculation. So, as we'll see in future modules, there are many naturally occurring situations where one variable quantity can be calculated, or at least approximated, from another quantity. Here's an example. Let's suppose h is the height in feet of a stone dropped from a height of 200 feet. And this little h is the height t seconds after it's dropped. The height in feet, t seconds after it's dropped. Well, you would expect that the height after t seconds could be calculated using t, and that is the case. H, the height above the ground, can be calculated using this formula. H is 200 minus 16t squared. This is a formula from physics, although we won't be doing much physics in our examples. In a situation like this, where h can be calculated from t, we usually say that h is a function of t. And we might write h of t is equal to 200 minus 16t squared to indicate that h is a function of t. So what we'll be doing with functions, one fairly easy thing is evaluating functions. So evaluating a function means doing the calculation or finding the output for some given input. For example, let's take this function described by the equation f of x equals 2x squared. And what I would like to do is evaluate this function when x equals 3. In other words, I want to find the output when the input is 3. The short form of this question would be simply to say find f of 3. Remember, if f is a function, then f followed by 3 in parentheses means the output when you use the rule for f with 3 as the input. And what do? We simply replace x by 3 in parentheses in the formula for f. That's the formula 2x squared. So if you do that, we find that f of 3 is 2 times 3 in parentheses squared. 3 squared is 9. Multiplied by 2 gives you 18. The parentheses around the input, so when I did this calculation, when I plugged in, I put parentheses around the 3. The parentheses are not always necessary, but sometimes they are. And in any case, it doesn't hurt to put them in. So I recommend always putting in the parentheses when you are evaluating a function. Okay, let's try a few more examples. Here is another function defined by the equation f of x equals 2 to the x. Let's find f of 3. How do you do this? You take the formula for f, You take the formula for f, which is 2 to the x, and replace x by 3. In parentheses, I recommend. This, however, is one of those cases where the parentheses are not necessary. And 2 to the third, as we know from our earlier discussion of exponents, is 2 times 2 times 2, which is 8. Let's try a slightly more complex example. So here's a function capital A of t. And the formula is 500 times the quantity 1 plus 0.05 over 12 raised to the power 12t. We have actually seen this function before. This is a savings formula. This would be the amount in a savings account that had an initial value of 500 and paid 5% interest compounded monthly at the end of t years. One other thing to note is that the input variable doesn't have to be x, and the name of the function doesn't have to be f. Right, here the input variable is t, and the name of the function is capital A. So what I want to calculate is a of 5. In other words, I want to find the output for the function capital A when the input is 5. So what I have to do is replace t by 5 in the formula for A. By 5 in parentheses, that is. So plugging in t equals 5, we get this expression. Same as the formula for A, except t has been replaced by 5 in parentheses. And so when I did this calculation, I got $641.68. And I did this on Desmos. Like you may have done this kind of calculation earlier in the course. Okay, we'll try this example. So g is the function defined by the equation g of x is 3x squared minus 4x minus 3, and I want to find g of 2. So this is a fairly easy thing to do. We're simply going to replace every occurrence of x in the formula for g by 2 in parentheses. And we get g of 2 is 3 times 2 squared minus 4 times 2 minus 3. So if you do this on Desmos or on a calculator, the calculations will automatically be done in the right order. You can simply enter things as they appear here in this line, this displayed line. If you're going to do it on with a pencil and paper, you've got to be sure that you do the operations in the right order. So what I'm about to tell you is something you probably already know. We're calculating g of 2, which is 3 times quantity 2 squared minus 4 times 2 minus 3. And what I want to do is look in detail at the order in which the operations should be done. There are standard conventions for the order of operations. And the first thing you do is any operations that are inside parentheses. Well, in this expression, we don't have any operations inside the parentheses. We just have numbers. There are no operations in parentheses in this example. And then you do exponents second. So there is one exponent here, the exponent 2 on the number 2. So the next step would be to square the 2. 2 squared is 4. So the resulting expression would look like this. Then you do the divisions from left to right. There are no divisions in this expression. And then you do the multiplications from left to right. Here we have 2 multiplications. There's 3 times 4, and there's 4 times 2. So I do the 3 times 4 first, and then the 4 times 2. The result will be 12 minus 8 minus 3. Then you do the subtractions from left to right. So we first subtract the 8 from the 12 and get a 4. And then we subtract the 3 and get a 1. And finally, you do the additions from left to right. And here again, there were no additions in this problem. So this is something you probably do automatically. Just a quick review of the conventions for the order of operations. Okay, let's try another example involving exponents. A of t is 100 times 1/2 raised to the power t over 4, and I want to calculate a of 8. We know what this means. We're going to replace t in the formula for a. Going to replace t by 8 in parentheses. And this is what we get. 8 over 4 is 2. Then we do the exponent. 1/2 to the second is 1/2 times 1/2, which is 1/4. And finally, we do the multiplication. 100 times 1/4 is 25. Fairly easy calculation to do on paper. Let's try a of 3. So now we are replacing t by 3 in parentheses, and to get a decimal answer, this will require a calculator, either a handheld graphing calculator or Desmos, possibly, some kind of technology. So on most graphing calculators, you would simply enter 100 times, and then 1/2 in parentheses, raised to the power, and then the exponent 3/4 in parentheses. On Desmos, you would enter this 100 times 1/2 raised to the power 3/4. This is what it would look like on the Desmos screen. And either way, the final answer should be 59.46. I rounded off to the nearest 1/100th, 2 places to the right of the decimal. Now sometimes we will get a function that's described by a table, as we saw earlier in this set of slides, rather than being described by a formula. So let's try an example. Let's say f is the function described by this table. This is the example we looked at earlier. And evaluating a function described by a table is a pretty easy process. Let's find f of 3. Well, the inputs are located in the top row of the table. So we find 3 in the top row of the table, and the number below 3 is f of 3. 7 is f of 3, or the output when the input is 3. F of 3 is 7. If 3 had not appeared in the top row of the table, then this would not have been a fair question. What is f of minus 2? Same kind of procedure. You locate minus 2 in the top row. Minus 3 is below minus 2. F of minus 2 is minus 3. And now let's look at one other fairly easy thing that we might have to do with functions. Suppose we have a function described by an English phrase. This is the example we saw earlier. F of t is the temperature at Willow Run Airport on December 3rd, 2019, t hours after midnight, given in degrees Fahrenheit. And suppose we know that f of 3.5 is 17. So what does this mean? Fill in the blanks. And here are the blanks. it was blank degrees Fahrenheit at blank hours after midnight on December 3rd, 2019 at Willow Run Airport. It was 17 degrees Fahrenheit. The 3.5 is the number of hours after midnight. So this is a relatively easy kind of problem that we might encounter. And now we are going to look at the graph of a function. I want to start with a brief review of coordinates. So coordinates provide a way of giving a name to every point in a plane. So you start with a plane, a flat surface, and the plane we'll be working on is the screen of your device or my device. And how do you set up coordinates? You choose a point in the plane, which we will call the origin, and we label it with the letter O for origin. And we choose a distance to be 1 unit. So doing those two things, your plane might look like this. I have chosen this point to be the origin, and here is my unit distance. Now, take some other point in the plane. I've called this other point P. It's sitting up here to the right and above the origin, but it could be anywhere in this plane. The coordinates of P are the pair of numbers consisting of the horizontal and vertical distances of P from the origin. So you start at the origin. You measure how far you have to go horizontally to get to P. That's 4 units in this picture. And then you measure how far you have to go vertically. That's 3 units in this picture. And those two numbers, that pair of numbers, 4, 3, are the coordinates of the point P. The horizontal and vertical distances of P from this point that we've chosen to be the origin. And you can measure the vertical distance first if you want. From the origin we go up 3 units and then horizontally 4 units to get to the point P. You can measure them in either order, but the horizontal distance is always the first number in the pair of coordinates. So in this example, the point P has coordinates. The coordinates of P are 4, 3. This means 4 units horizontally and 3 units up from the origin. And we usually, when we're doing coordinates, we usually insert a horizontal line through the origin. I've done that here, called the x-axis frequently, and a vertical line through the origin, called the y-axis. We put a distance scale on these two axes. So here is the point on the x-axis, 1 unit to the right of the origin. Here's the point on the x-axis, 2 units to the right, and so on. The point labeled -1 is the point on the x-axis, 1 unit left. -2 is 2 units left on the x-axis, and so on. And then it's also helpful to add these grid lines. Those make it easier to approximate the coordinates of points in the coordinate plane. So what we see here is really a completely drawn coordinate plane. So we would call P the point with coordinates 4, 3. Or we might simply say the point 4, 3. And one thing to keep in mind is that in assigning coordinates to points, if you go to the left of the origin, the distance is negative. And if you go below the origin, if you go from the origin to below the origin, the vertical distance will be negative. So a point that is left of the origin will have a negative first coordinate, and a point that is below the origin will have a negative second coordinate. We will see examples of that occurring shortly. So every point in the plane has a name, its coordinates, and the thing that this does for us is that it enables us to draw pictures or graphs of functions. A picture of a graph, a picture of a function in a coordinate system is called the graph of a function. Let's see how this works. This is a procedure that you have no doubt seen before. So let's try drawing the graph of this function with a fairly simple formula. F of x is x squared minus 1. So you set up a coordinate system, and you think of points on the horizontal axis. You think of points on the x-axis as representing inputs. So the points on the horizontal axis are the replacements for x. And then the height of the graph above each point on the x-axis, each point x on the x-axis, will be f of x. So the height of the graph above an input number will be the corresponding output. To try a specific example, we'll stick with the function f of x equals x squared minus 1, and we will find the height of the graph above the number 2. So we're thinking of 2 as being an input. What is the height of the graph of this function above 2? It's the output corresponding to 2. It is f of 2, which is fairly easy to calculate. 2 squared minus 1 would be 3. Okay, so here's a graph with nothing really drawn on it other than the coordinate system at this point. So we're thinking of the number 2 here on the x-axis as being an input, and the height of the graph of the function f above 2 will be 3. So here at the point 2, 3, we will have a point on the graph. So what is 2, 3? It's the point whose horizontal coordinate is the input 2, and whose vertical coordinate 3 is f of 2, is the output corresponding to 2. So far I have just a single point on the graph. To get the entire graph, we want all points that look like this. All points whose first coordinate is an input and whose second coordinate is the corresponding output. For our function f of x equals x squared minus 1, the green curve is the graph of the function. How do you go about actually graphing a function? Well, one possibility is to find several points on the graph and then connect with a smooth curve. Basically, you would be trying to guess what happens in between the points that you found. But we will primarily be using technology to draw graphs. Graphing calculators, including Desmos, make drawing the graph of a function fairly easy. And actually, I used some technology to get that green graph on the previous slide. If you're using a TI graphing calculator, you begin by pushing the y equals button. And then you enter the formula for the function on the right side of an equation. You will see y1 equals. So after pushing the y equals button, you will get a screen in which the left-hand column has at the top y1 equals, below that y2 equals, below that y3 equals, and you can enter up to 10 functions on a basic TI graphing calculator. We will probably only be using the first. So enter the formula for the function on the right-hand side of this equation. And then you push the graph button, and the graph of the function will appear on the display. The variable that you use in the formula must be an x, and you enter x when you are entering the formula by using the key that's labeled x, t, theta, and n. On Desmos, I think things are easier. You simply enter the equation in one of the calculation boxes that appear in the left-hand column. We'll look at an example very shortly. So, for example, if you wanted to graph the function f of x equals 1/2 x squared minus x minus 1, you would enter in one of the calculation boxes y equals 1/2 x squared minus x minus 1, just as it's written here in the definition of f. So this would be one possibility for getting the graph of this function on Desmos. Desmos is actually more flexible than that, as we will see in the next slide. So here's a screenshot in which I have entered three different functions using three different options on Desmos. So in the first calculation box, I simply entered y equals 1/2 x squared minus x minus 1. A lot like you would enter on your graphing calculator. And when I did that, the graph of this equation, in red, because the red circle is to the left of the equation, the graph of this equation appeared in red on the screen. It's this red parabolic shape. But Desmos allows you to use variables other than the usual y and x. For example, in this second box, I used b instead of y and a instead of x. And I entered the equation b equals 2 minus a squared, which appeared in blue, as soon as it was entered. It's this parabolic shape in blue. And a third possibility is to enter f of x equals, and then the formula for the function. I did something fairly simple here. I entered f of x equals x plus 5. This was graphed in green. You can tell because of the green circle here to the left of box 3. And it's this straight line that appears on the Desmos graph in green. So when you are graphing, my recommendation is to use Desmos, although Graphing Calculator will certainly work. Okay, one thing that we will have to do on occasion is evaluate a function from its graph without having an equation for a function. Just having the graph. How do you find outputs, or at least estimate outputs if you're given the input? This is a fairly easy process also if you remember how a graph represents a function. So let's try this problem. I have the graph of a function, and for this function, whose graph will be shown in just a second, I want to find f of 3 and f of minus 2. Okay, so here's the graph drawn in green. Let's work first on finding f of 3. So we locate the input on the horizontal or x-axis. Here is 3 on the horizontal axis. And f of 3 will be the height of the graph at 3. And if the graph is below the x-axis at 3, f of 3 will be a negative number. So this place where I have my cursor is the point on the graph directly below 3, and the distance from 3 on the x-axis to that point on the graph will be f of 3. And it will be negative because the graph is below the x-axis. So this point is the point with coordinates 3, f of 3. So now we get to the approximation part. How far below the x-axis is that point? I am guessing 1.8 units. So the point on the graph directly above or below 3, it's below in this case, is approximately 3 minus 1.8. So that would mean that f of 3 is minus 1.8. And when you get the value of a function, when you evaluate a function using the graph, you have an approximation. What about f of negative 2? Well, that I didn't do. But you can probably tell me what it is. Let's see. Here is negative 2 on the x-axis. F of negative 2 will be the height of the graph above negative 2. My guess is 1.